Our last lecture of the morning is the last lecture of the conference, and it's given by Carola Schönlein, and she's going to talk on optimizing the optimizers.
Okay, thank you very much, and thanks a lot for inviting me. So I should say that this is joint work with a couple of people. So the whole project started together with a colleague of mine from Quito, Juan Carlos de los Reyes, and then the follow-up works that we did on this topic were together with one of my students, Luca Calatroni, and Tuomo Valkonen, who is a postdoc in my group. Okay. Good. So what is it all about? Let me just start with some basics. So the basic that the basic problem that we all consider, that we all face, is the generic inverse problem, which is the following. So you have some data f that you observe that is potentially corrupted by noise or undersampling, and what you want to do is, based on your knowledge of the data f and on the knowledge of how this data f is related to the quantity you're actually interested in, you want to recover this quantity that I call u. And this relation between f and u can be linear, can be nonlinear, can again model corruptions like noise or undersampling and things like that. Okay? So this is the basic inverse problem that we all look at, basically. Okay? And of course, the ones that we are interested in are mostly ill-post inverse problems where the operator t is not invertible. Okay? So what you do usually, or the kind of approaches that I will consider, is you want to turn this ill-post problem into a well-post problem by adding some a priori information on the quantity u that you want to retrieve. And one way of doing this is variational regularization. So now you phrase your problem as a problem where the quantity that you want to compute is a minimizer of a functional that generically looks like this. So first of all, you have a term that I call here data fidelity term, which takes the forward model, so takes your relation between your measurements f and the quantity u, and penalizes some sort of distance between the two things. And then you have your a priori information, which in the kind of examples that I will look at is given by a certain regularity that you assume your quantity u has. Okay? And then, of course, you have to balance the two guys against each other, and this is encoded here in this parameter lambda that will determine how much do you trust your forward model in comparison with how much do you have to add a priori information to make this problem well posed. Okay. So just to stress, so when you're faced with one particular inverse problem with a particular application, when you have a particular application in mind, you have to decide upon certain things in setting up your model. Well, first of all, you have to decide on the kind of prior information you want to feed your inverse problem with, and this can be modeled in terms of, as I said, regularity of the quantity that, well, in my case, will be an image. You want to reconstruct can be in terms of, well, let's say basis functions. You assume your image can be expanded in, and then, of course, there are many more things, of course, related to a priori information. Nowadays, in quite a lot of things that we look at is sparsity. So let's say you assume that your image function is just encoded by a very small number of basis functions, for instance. Okay. And then, of course, the forward model, which is usually derived from your physical understanding of how u and f are related with each other, maybe you can derive this relation of how exactly this is related from some statistical considerations or some heuristics and so on. Okay. Okay, so this is the basic thing. So now what I want to discuss is a slightly different approach that people in machine learning have followed quite a lot, or are following quite a lot, which is that both of these things you could potentially also think about learning or deriving directly from the data. So what does the data tell you in order to come up with the right image and data model? Okay, and this is the thing that I want to discuss. Okay. Okay, so optimize the optimizers. What does it mean? It means how can I come up with an optimal modeling for a particular inverse problem I want to solve. Okay. And in what I'm going to discuss, I will simplify my life a little bit now, and I'll just consider image denoising, where in this case the operator T just models degradation by noise. So for instance, if your noise is additive, then F, so the image, the noisy image that you measure is just U plus a noise component. Okay. Okay, so this is where we start now. Okay. And that's the outline. So let's see. Yeah, please don't be shocked by the number of slides. I'm not expecting to go through all of it. Okay. Okay. So what I start with is first of all trying to learn the data model in an image denoising problem. So here I fix the prior information by saying what I assume is that my image U that I want to derive has a small total variation. Okay, and this is not because I think the total variation is the holy grail in inverse problems, but just because well, it is a very powerful tool, let's say, in imaging, in inverse problems related to imaging, and one of the standard regularizers. So that's what we fix for the moment. So here in the first part, I'll just look at a total variation denoising model, and I want to learn from the data, the fidelity terms. Okay. So I want to learn the forward model basically here. The second point is related to the first one, where I want to stress, basically I want to raise the issue that when you want to learn from data, usually what you want is to derive an optimal choice that is robust. So you base your optimization in an ideal world, let's say, on a very large database from which you want to learn. And then, of course, there are some computational issues here. So if we get there, then I will discuss this. And then the last point is that of learning the prior, or understanding more about a prior that is applicable to a particular set of images. And here I will discuss the particular setup of a generalization of the total variation of this total, what is also called total generalized variation, which is some kind of combination between first and second order regularization of the image. Okay, so that's the setup. So let's start again, and let me just again raise what in image denoising are the main ingredients of a variational regularization model. So as I said, in this case, the correct data, correct forward model is in particular the noise model that encodes the type of noise, the distribution of the noise or the distribution of the data that you assume your image is corrupted with. The correct a priori regularity assumption, so what do I assume are the intrinsic features of the image I want to preserve while doing this denoising process, and then of course the balancing between regularity the balance between regularization and sticking to the forward model. Okay. So as I said, here we will just concentrate on the total variation as a regularizer. So the regularization problem we consider is this one. So we have here the total variation as a regularizer, and here we have just a generic fidelity term, so a distance between the noisy image f and the denoised image u, and the weighting between the two. So this is what we have already seen before, just that I've fixed now the regularizer. Okay. So just as a motivation, why the total variation in imaging, I already said, is a kind of a standard, one of the standard tools in imaging, in mathematical imaging, and that's just because if you have a situation like this, where this is a simulated example, so I have my original image here, I have my noisy image here, so I corrupted this with some Gaussian noise, and you denoise this image just basically by Gaussian filtering, so a very, very simple filtering method, and you compare this with a candidate denoised image that was optimized using the total variation as a regularizer. You immediately see the advantage, namely that the total variation is able to preserve certain structures in the image, in particular image edges. Okay. So that's why we fix it, and now the question is, what can this fidelity term be? And again, as I said, this will depend on the type of distribution of the noise you are looking at. So for instance, if you have normally distributed noise, then a standard choice for phi, or actually what comes out from the statistical modeling, is just to take the squared distance between u and f. If you have impulse noise, so just noise that is concentrated in a few pixels of your image, then a standard choice is the L1 norm between the L1 norm of u minus f. And then there are more. So if you have Poisson noise, then you have something that is also called the Kullback-Leibler divergence, which is this term here, and there are many more noise models that you could think about. Okay, so these are just 3 examples, and I just give those 3 examples because these are the examples we will look at. Okay. Okay, and then so now we have fixed this. Now I've given you a few choices of this, but what is now really the influence of this parameter lambda? And although here the lambda is inside of the integral, so could potentially be spatially dependent, so a function on omega. For all the examples that I'm going to show you at the moment, lambda is just a constant. Okay. So what is the influence of lambda? Well, as I said, lambda balances regularization against the trust you have in your image f, in your noisy image f that you acquire. So if you start with this noisy image here, and you start with a rather large lambda, which means you trust the image f that you look at very much, and you don't regularize a lot, then you get an answer like this. If you decrease lambda, so here I start with a large lambda, now I decrease lambda when I go from here to here, then you see that you regularize more and more. And the point that I want to make on this slide is that the choice of the lambda is crucial for deriving a denoised image that is still close enough to your noisy image in terms of it still has some of the structures you see here, some of the intrinsic structures that are not noise are still present here, while the noise has been reduced well, sufficiently, let's say. Okay, and this is of course objective. Okay, how do you choose the lambda? What is the best choice here? Of course, you might agree that this hasn't been regularized enough, and you might also agree that this has been regularized too much. But that this is optimal is of course questionable. But this is, well, this is basically the discussion I want to make here. Okay. Just some remarks here about how this lambda is usually chosen. So I think, just to be a bit provocative, I think in most cases lambda is just chosen manually. Okay, so by trial and error, basically. But there are approaches which somehow relate the choice of lambda, first of all, to the noise level. So there are some statistical approaches which relate lambda to, let's say, if you have a normal distribution, to the standard deviation of the normal noise distribution. And of course, also in this case, we have machine learning approaches that I will not discuss now, but where you try to learn without knowledge of sigma, you try to learn the regularization parameter or the setup of your model from the data itself. Okay, and this is also the kind of philosophy we want to look at here. And how we are phrasing this is in terms of a bi-level optimization problem. Okay, so let's look at this. For that, first of all, we are going to extend the denoising model that you have seen before by giving it a choice of different data fidelity terms. Okay, so now instead of just having one data fidelity term, I write down a sum of data fidelity terms that are weighted against each other and against the regularizer, against the total variation, with these regularization parameters lambda I. Okay, and sorry.
The phi i's are assumed known.
The phi i's are known, and so this is the problem, the generic, let's say, denoising problem that we look at gives the choice of these three data fidelity terms. So Gaussian noise, impulse noise, and Poisson noise, and as I said, they're weighted against each other with those lambda i's. Okay, so this is the generic model we start with, and now the goal is to understand what is the right choice of the lambdas. Okay, and for that, okay, actually, let me go to the next slide. That's not too important. For that, we start with the following. So let me stress that for what I'm going to tell you, the only ingredient that I need to feed my optimization method with is this training set, a training set of measurements, Fk, and well, let's say ground truth images, Uk. Okay, so that's the only ingredient. I don't insert any knowledge of what kind of noise is there in Fk and Uk, but for this optimization, what I assume is that Fk and Uk for a particular number of training pairs are all following the same distribution. Okay, so this is the only information I have. And then what I want to do is the following. So now I want to derive an optimal choice of the weightings of these different data fidelity terms against each other. So weighting of, I want to derive an optimal lambda vector, let's say lambda 1 to lambda 3 in our case, in terms of, well, what means optimal, and this is again relates to this slide where I've shown the effect of the lambdas. So optimal in terms of, I want it optimal that the regularized solution that I get from my total variation denoising problem is closest to the ground truth image. Okay? Is that clear? So what I want is I want to derive an optimal choice of the lambda vector in my total variation denoising problem by minimizing the distance in terms of the L2 norm between my candidate denoised image that is derived from this total variation regularization model and the ground truth image. And potentially what I want is I want to derive one lambda vector for this whole training set, okay, that is applicable for this whole training set of images. Okay, so this is where I start from. Just a few words on related contributions. So I said on a couple of slides before that this idea is, of course, not new in the machine learning community. So there is work by Tappan, which looks at also some kind of bi-level optimization problem using Markov random field models. There is also some work in the PDE community where those guys here look at, again, a bi-level optimization problem of setting up an optimal differential operator in a PDE regularization approach. However, so they have very promising numerical results, but no analytical justification. And then, very related to what we are doing is also recent work by Kunish and Pock, where they look again at a bi-level optimization technique to learn an optimal regularizer, where again they give different choices of regularizing functionals. Okay. And they want to understand the right balance of one regularizer against the other for a particular set of images. Okay. So our goal is we want to state and treat this non-smooth optimization problem, so this bi-level optimization problem in function space, so in the continuum. For that, we want to derive Lagrange multipliers and optimality conditions, which characterize an optimal solution of this bi-level problem. And eventually, what we want to do is what I'm going to show you is going to compute now then these optimal weights with a fast derivative-based and mesh-independent optimization method. In particular, what we will look at is a quasi-Newton scheme. Okay. Okay. So, just for me, for simplicity, I'm going to just concentrate on one training pair here. The analysis goes through in a similar way if you have more training pairs, but then I just don't have to write the sum all the time. So now I have the same problem as before, but I just have one training pair here. And for simplicity, I'll just for you to show it here, I'll just have the L2 data fidelity term for U minus F here. So one thing that has changed now to what I've said previously is that now what I'm doing here is I regularize the problem a little bit, okay? And the reason why I'm doing this is that if I do this, then I can work in a Hilbert space, okay? And working in a Hilbert space gives me a much stronger topology for proving, well, existence of solutions to this problem, but more importantly, actually something that we will need later on, continuity of the solution operator in terms of, so the continuity of the lambda when I basically continuity of the solution operator that maps U to a U of lambda that maps the lambda to a U of lambda when I change the lambda. Okay. So this is, and of course, again, when we look at the computations later on, the epsilon, you want to choose the epsilon very small, okay? Which you can do. It doesn't.
Also regularize the lambda.
Yes, but that's actually, yeah, you don't have to do it. Okay, so yeah, so two things. So here I still have this regularization in there because we did that at the beginning. If the two things. If the lambda is just a vector of scalars, then you don't have to do it. Okay, then you can forget about this at all. If the lambda is spatially dependent, then you can still get rid of this, but you need some L infinity constraint on the lambda, on the lambda function. So you don't really need it. Yeah, because one thing that you could argue is now you have to choose something else. Yeah, but you don't really need it. Yeah, I should update the slides, but you don't really need it actually. Yeah. Okay, so if you look at this, you can reformulate the lower level problem here in terms of a variational inequality that now looks like this. Well, didn't change anything, but and now of course you can extend that again, with this variational inequality, to multiple noise models. So this is what you see here. But although, and we can prove existence of an optimal solution. So so you can prove existence of an optimal solution for this problem. But, and that's at the very bottom here, although we have regularized this problem now in order to shift the problem into Hilbert space, it is still non-smooth. And why is this problematic? It's still non-smooth because the total variation is non-smooth. Okay. Why is this problematic? So there are general works, not very much, but there are some general works on how do you solve bilevel optimization problems when you have a variational inequality that is also called a variational inequality of second kind, where you have non-differentiable terms in it. But the problem is that this general theory, if we want to apply that to our problem to derive optimality conditions, then the general theory doesn't give you an optimality system that characterizes the solution uniquely. So what I say here, it's not sharp enough. So for instance, if you look at a general problem where you have, which involves a variational inequality that now, in our case, this is just the gradient of u that has a general convex functional in it that is non-differentiable, then the kind of optimality condition that you can derive from this general theory results in ambiguous situation in terms of the solution. So the subgradients Q are not, for instance, are underdetermined. This is the word I was looking for. Underdetermined in the places where in our case the gradient of u is 0. Okay, so that's not sharp enough. So what can we do? Well, we use the special structure of the total variation and we regularize once more. So what we do is we replace the total variation by a Hoover regularization, so-called Hoover regularization of the total variation, which is also called active-inactive set regularization strategy, where you only smooth the total variation in the region where you have problems, so around 0. And the difference to doing a regularization, well, let's say the total variation gives you the possibility of really tailoring your regularization to the non-smooth functional you're looking at, in terms of you don't have to regularize everywhere, but just in the place where it's needed. Okay, and this is this Hoover regularization functional that we are looking at. Okay, so if you do this, okay, it's just a message, it's not the same thing. If you do this, then you replace your variational inequality by an equality, and here you have this Huber regularized gradient in it. And now this is an optimization problem now with nonlinear PDE constraints. Okay? Good. And for that problem, we can say much more. So what can we say? First of all, for a fixed lambda, so just to tell you what the approximation properties is, for a fixed lambda, the Huber regularized solutions converge to the solution of the TV problem that was transferred to the Hilbert space. Then we can get continuity of the solution operator. And as before, we can derive existence of a solution of the TV problem, of course, but also of the whole bi-level optimization problem. Okay? So that is nice. What is even nicer is that the whole problem is differentiable. So we can prove that the solution operator is differentiable, and by using this, we can derive an optimality system for the problem. And don't read everything here. It's not that important. What is important is, because we have the optimality system, we can actually characterize the gradient, which we will then also use in the numerics. Okay. And so I said before, we are Huber regularizing the total variation in order to get a well-posed optimality system. And actually now, within this, having this optimality system, now we can go back to the original problem by letting lambda go to infinity, and we can derive an optimality system for the epsilon TV problem that we have started with. Okay? Okay. Yeah, so last comment actually to what Adrian said. So we have this regularization in here, but we don't really need it. So if the lambdas are just scalars, we can set that to 0. Or if they're spatially dependent, replace it by an L infinity constraint. And one thing that Luca actually looks at the moment is maybe sometimes you actually want some regularization, but maybe not, as in the case we had before, just an L2 regularization, but some kind of sparsity constraint on the lambdas. Because since eventually what we want is to have a denoising problem which is very generic in the sense that you have a couple of denoising fidelity terms that you want your method to choose from. But let's say the images that you have in your training set are just corrupted by normally distributed noise, and ideally what you would like to have is you would like to get an optimal lambda vector where just one of the lambdas is non-zero. Okay? So you could think of enforcing this by a sparsity constraint. Okay? Okay, what's the numerical strategy? So what we do is we use a quasi-Newton type method to solve this problem, in particular a so-called BFGS method. The lower level problem we solve with the Newton type algorithm, so in particular semi-smooth Newton algorithm. The gradient of the cost functional, now we can use the adjoint information that we got from the optimality system to evaluate that. And for the update of the BFGS, so for the update of the quasi-Newton scheme, we are using an Armijo line search rule. Okay. So that's if you're not too familiar with quasi-Newton type methods, you can ignore it. But just for the ones who know about it, some details. Yes.
Another BFGS, or you consider something for non-smooth, like a...
No, just the conventional. Well, actually now, sorry?
Because you already used the Huber in order to...
We use the Huber regularization, exactly. Yeah. Yeah, let me actually also say that what Kunisch and Pock did, right? So just in relation to what we did. So the only reason why we need this H1 term here, why we need to shift this to the Hilbert space, is because we are in the continuum. If you do all your analysis in the finite dimensional case, you discretize and then do your analysis, then you don't need that. It's just because we need a stronger topology for what we are proving. Okay, so and Kunisch and Pock did everything in finite dimensions, so they don't need this epsilon term. Right, so first thing we tried is just a simple parameter selection for the problem when we just have one data fidelity term. So we just have we just have a model with normally distributed noise, and the only thing that our algorithm is choosing now is the weighting between the regularization, and the data fitting term. Okay. So what do we get? Just to look at some examples. So here we have two images, two training images. One of them has, one of them is more noisy than the other, let's say. And on the right, you see the optimally denoised images. Okay. And now again, optimal is of course in terms of the least squares error. Okay. Between the denoised image and the original one. Okay. So what else? Yeah. Because of our choice of the cost functional, because of our choice of the optimality, what do we mean by optimal? So what do we mean by the reconstruction is close to the original? Of course, we get optimality also in terms of certain quality measures that are now famous or infamous in the meanwhile, actually, in the imaging world. For instance, the signal-to-noise ratio is, of course, then also the highest for our optimal choice of the lambdas, but that's just because how we chose the cost functional. Okay. In this example, we have two data fidelities. So we have an L2 data fidelity for potentially normally distributed noise, and we have this Kullback-Leibler term for Poisson noise. And now let's look at an example when we do this. So here we really have Poisson noise and Gaussian noise. So what we did is we first corrupted the data with Poisson noise, and then we added some Gaussian noise to it. Okay. Okay. So maybe some comments will come later, but if not, then I will not comment on this. If yes, then yes. Okay. But so anyway, this is our result. So this is the noisy image. This is the original one, and this is what you get as an optimal reconstruction. Okay. Impulse noise. So here you also see how impulse noise looks like. Again, actually, yeah. Again, this is the original one, and this is the optimal denoised image that we computed. And now, yes. So I have 5 more minutes or so, I guess. Okay, so actually maybe I don't talk a lot about this because I just want to have more time for discussions. Let me just say that if you want to do this now, not just for one image, not just base your optimal optimal parameter estimation on one image, but on a database of images, then of course what you have to solve is a bi-level optimization problem with a system of PDE constraints. And that can be quite costly, well, depending on how many PDE constraints you have, so how large your database is. So you can, in this case, this is, well, these are examples of the database that we looked at. So here you just have some noisy brain images and the original ones, and this is part of the optimally computed denoised images that you get. So just to show you that it also works for that, and actually let me now go to some future directions. So first of all, I already said that we would like maybe to have an L1 a sparsity constraint on the lambdas. in order to deal with situations where the model is very rich, but actually the images that you feed it with are just, the corruptions are explained by just one of the data fidelity terms. Also, what we were thinking about is, of course, it would be nice also to go more towards really inverse problems. And the first thing we wanted to look at is deblurring. We also wanted to look at spatially dependent lambdas. For instance, if you have situations where the noise is concentrated in just parts of your image. And then the last thing I just want to show you is what can be done in terms of choosing the correct regularization. Okay, and here we looked at, as an example, at TGV regularization. I don't want to say much about TGV regularization. The only thing I want to say is that with total variation regularization, what you're penalizing is our first order features. So with the total generalized variation, you balance first order against second order regularization, and you do this in a clever way. Okay, and why is this sometimes important? Let me actually show you the TV regularized solution for this case. I don't know if you can see that, but with the first order regularization, like the total variation, what is good about it is that you can, as I said, while denoising, you preserve the main structures in your image, sort of let's say the outline of the objects that you have in your image. So the image edges are recovered exactly, but what you're basically doing when you compute the TV regularized solution is you approximate your original image by a piecewise constant function. And sometimes this is not the best explanation for an image, because an image doesn't just consist of piecewise constant parts, but maybe you have some linear parts in it. And then it still tries to do that, and this is also what is called the staircasing effect. So you have these blocky-like structures that look like this, and then it pays off to involve higher order regularization, because then you extend your point of view of piecewise constant images to piecewise linear images, and maybe if you increase the order of your regularization even more to quadratic and so on images, okay, basically, in simple words. So this is what you get when you optimally choose alpha and beta in this TGV regularized, with a TGV regularized solution, and you can see that these blocky features are now eliminated in this case. Okay, good. So I think, are there, at the moment, questions? Maybe later. So to conclude, what we discussed with is a type of machine learning approach, but that works on a functional model like the total variation regularization model. And in particular, what I've shown you now is an optimal choice of weights between different denoising models in between different denoising models in a generic total variation regularization approach. The main message that I want to give here is, just because we are analysts, actually not just because. So one reason why we wanted to analyze this in the continuum is just because we have this point of view of optimize and then discretize, and this eventually gives you conclusions which are independent of any discretization. But also because the analysis is just more beautiful if you do that in the continuum. I've already told you some future directions. So of course, a general, at the moment, linear operator might be nice to have in the problem as well. And of course, there are I mean, there are basically no limits of what you could envision where this might lead to. So the question is, how general can you make your model basically, and still being able to get some optimal answer out of that. And with that, I thank you very much for your attention, and yeah, thank you. Yes.
One is putting that little epsilon Laplacian in. You said you needed it for the math. One can argue whether with harder math you might not, but the question is in practice.
Yeah, the continuity was the problem for us. We couldn't show the continuity without the epsilon. So the existence actually still goes through without the epsilon.
Right. No, but the question is
yeah.
in practice. What happens? You must see what happens with the epsilon and how much your answer depends in the numerics on the epsilon.
Yeah, you don't. So the epsilon actually we chose very, very small.
Okay. And if you make it 0, because I mean, if it's there for the math, what happens in the numerics if you make it 0?
Okay, that's a good question. So the point is also in the detail of the BFGS algorithm, because for this quasi-Newton type method, you need basically a stable. Well, you need a stable estimation of the Hessian, basically, and that's. Actually, I'm not sure if Luca has tried it with epsilon equals to 0, but I would think that something would break. Then we would have to change our optimization strategy. Actually, maybe again to use some semi-smooth Newton at the outside.
My other question, I hope you don't find it unfair, is this. Let me make it a value neutral question. Are there situations in practice where you do have training data available?
Yeah, that's a good point. Yeah.
Because if not, then you're taking images, you're noising them as you like, and then this might just produce the lambdas that correspond to how you noised your images. And so it's not data driven; it's driven by your learning.
Well, that's all simulated, of course. Yeah.
Right.
Yes.
But I mean, when do we ever have the full truth?
Okay. Okay. So one thing that we were thinking of was if you think, for example, to applications like MRI. Well, let's stick to MRI. Let's say. Then you can, well, depending on how you set up your MRI experiment, how you set up the acquisition, will determine the type, well, the strength of the noise that you get back. So you can be as accurate as you want, depending on the amount of time you're measuring. Basically, you are acquiring the data. So if you think about tuning a reconstruction approach for some clinical MRI application, let's say, then you could think about, you just take a phantom, one of these MRI phantoms, and you create your database first by just acquiring this phantom with very high accuracy, so not in the usual clinical setup. And then you do the same, but with a usual clinical setup, let's say. So you have your basically ground truth, which are of course not ground truth, but are very an estimate to ground truth with very high precision, and you have the noisy versions as well. Noisy versions, yeah. So this is one example. I don't know, in photography, it's the question, right? You can always, I don't know, you have a picture and you take a photograph of this picture and then you take the picture as the ground truth or something like that. I mean, I don't know. At the moment, this is still quite academic because we didn't go into applications yet, so we didn't look at that. And another thing, let me just mention one more thing. And another thing is that in certain applications, the type of images that you want to retrieve from your data, you might have some very good physical modeling for the type of images that you want to retrieve. So one example is fluid flow. So there are certain applications where people use MRI to they use MRI to visualize the velocity of a fluid. Okay, so they can again set up an experiment such that what the image that they get out encodes the velocity of this fluid. So this is a time measurement, of course. And then one thing that they are doing is they are simulating the kind of data that they expect to have just with basic CFD computations. So they are actually even doing this for setting up their experiments by hand. So they look at how does the fluid behave in general, and how do our reconstructions look like. So there are, even without this formalism, there are people who look at, well, how does our reconstruction compare to a potential ground truth? Yeah.
Would it be better, instead of TGV approach, to apply the standard approach to the gradient of the image and then reconstruct image from smooth gradient?
Yes. Yes. It's debatable, right? Because people have done this, what you're saying already, for quite a long time. So basically taking the total variation of the gradient. The only problem if you do this is that then you cannot reconstruct edges anymore exactly. Because you force your image immediately, your image will be continuous. So it will not be allowed to have jumps anymore.
I disagree, because it depends how you reconstruct the image from smooth gradient. You reconstruct it in L2 sense, then yes, you lose edges. If you reconstruct it,
no, I mean we can discuss later, but you're losing the edges. I mean you lose them to a certain extent, of course, only because depending on how much you regularize. But analytically, your image is continuous now. Yeah.
Your high-level optimization scheme is probably not convex in the regularization parameter, like in the lambda. You take this into account?
No. Well, no. So, or what do you mean by taking this into account? So,
using something like from non-convex optimization, or like, I don't know, that the initial estimate is important.
The initial, what we are doing at the moment is just initializing with the noisy image, basically. So you initialize your iteration with the noisy image. It is non-convex, so you get a local minimum. That's
I was talking about the higher scheme, like sort of what's your initial estimate for your lambda, because it's probably not convex in lambda. So.
Yeah. Okay. Of course. Well, yes. So we did some tests actually with that. How much does it depend with TV? With the TV lower level problem, it seems to be quite robust, and we don't know why. So we get more or less always the same answer. With TGV, it changes. So it depends also on the structure of the lower level problem. Yeah.
Actually, in image denoising, there is kind of state-of-the-art approach, non-local means. Can you compare you probably know that, right?
Yes, I know that. Yeah.
Can you compare?
Well, we can try. I mean, we haven't done it, but yeah. I mean, as I said, we just focused on TV because, well, kind of like it, and.
So let's thank the speaker again.